Well, I'm starting the recorder right now, and so are there any questions about the homework assignment? Okay. Yep. Go ahead.
How are we supposed to use the variable number and a number of colors? I'm not sure how to use that.
Okay. So the number of colors may not be that one is not useful because your job is to match the colors. It depends on your implementation. Okay. It depends on your implementation. You can use a invalid color, as a marker and say, okay, this particular peg has been matched already. Do not match it again. So that's one way to do it. But there are other ways to do it as well. So depending on your implementation, the number of colors may or may not be useful. Okay. Another question? You mentioned that you had questions about the homework assignment.
Well, my question is that my actual code, I want to wipe the white things, so it won't read it. So my program it escaped that line. I don't know why.
It cannot. Okay, maybe that's something we can take a look at, during the lab time. So it can actually show me the program, during lab time.
Yeah.
Okay.
Yeah. So you want to.
Any other? Okay. So are there any other questions regarding the general approach of the homework assignment? No questions? I'm assuming that you guys have at least, started with the homework assignment or started thinking about a homework assignment. Okay. Because, this is one of those things where you really should start early, think about it early. If you're done with it early, good. If you need more time, starting early will give you at least more time to work on it. Okay. So if there are no questions about the homework assignment, what I'll do today is to finish up the topic of strings, and particularly, we go back to C strings here, and I did not quite finish this whole thing because, I mentioned down here, there are these subroutines that I would, implement during class. So there's string copy, string compare, string and copy, string and compare, and so on. In-class demonstration is to write string copy and string and copy, string compare and string compare and string and compare. We did a compare already. Okay, the other day we did string compare. So what we'll do today is to deal with string copy, and we might even think about implementing string, which is a subroutine to find a substring within a string itself. Okay, so you're finding what we call a needle in a haystack. That's actually how they call those parameters, okay, by the way. So we will go ahead and take a look at some of these subroutines. We'll start with string copy, okay? String copy is just copying a string into another string. Can someone remind me what exactly is a string? There are two concepts mainly that you need to understand about a string that then you can implement all of these subroutines. What is a string in C? It's an array of characters. Very good. That's the first one. And then the second one has to do with, well, how do I know where's the end of the content of a string?
The null terminator.
A null terminator, which is a 0 byte, okay? A byte with 00000000 as the binary bit pattern. Very good. Okay, so those are the only two things you need to know. That basically defines what a C string is. It's an array of characters. One character is 1 byte, 8 bits, and it has to be null terminated. Okay, so the length of the array itself is irrelevant. Okay, that is completely irrelevant. A string is terminated by a null terminator. Okay, which can lead to problems. So what I was doing in the office right before class was I'm trying to write an exploit. Okay, remember the other day we kind of talked about Stack Overflow exploits, how people can craft a image file to break into Windows and stuff like that. Do you guys still remember that? Okay, so I was trying to craft something that would actually work in Linux, so that when this file is read, okay, it will cause the program to print a message that says you are hacked. Okay, that's all I want to do. Okay, I don't want to open a shell or do anything that's nasty, but just to get control and display that I got control of the program. Okay, I'm still in the process of working on it. Okay, it should be done by next Monday or so, okay? Because it has to be done in assembly language programming, and it has to be like a very specific type of programming as well. So I have to kind of craft the bytes that go into this particular file. But next Monday we might actually have a chance to take a look at an actual application of an exploit, okay? Which I think would be kind of fun, for this class, and at the same time gives you an idea of what an exploit is and why do we have to write programs carefully and why we don't want to use string copy. Instead, we should use string and copy. Okay. All right. So back to what we want to do today. The first one is string copy. String copy, as the name implies, is just copying a string to another string, which is, well, it sounds like something that should not need to be done by a subroutine. I mean, wouldn't the assignment operator do something like that already? That's the question. So let's go ahead and take a look at a sample program to illustrate why the assignment operator is not going to do it. Okay? So what we'll do is we'll write a simple program. Okay? So I'll make a folder just for string copy. And in here, we write a very simple program. And we'll say int main. Did I talk about how to initialize a string? Okay, it is in the notes. I might not have mentioned it, but if you go to initializing an array, this particular link will give you the notes of how to initialize an array. Well, maybe we should go over this one first because it does give us a little bit of, it's handy to know this, okay? All right, so this one has to do with the initialization of a string. This is one way to do it. In other words, on the first line or the second line, int prime 5 is basically declaring an array of 5 integers, and the name of the array is prime. So if I want to initialize this array with the first 5 prime numbers, this is one way to do it. I just spell out the assignment operations, like prime bracket 0 equals 2, prime bracket 1 gets 3, and so on. Okay, that definitely works, but it's cumbersome because I have to spell out prime open and close bracket equal to on every single line. I mean, this is really kind of repetitive and boring. And the worst part of this is I can make mistakes and the compiler will not be able to catch it. In other words, if I mistype this 4 here to be a 3 or a 5, the compiler cannot catch it and say, hey, tech, I think you meant 4. Nope, the compiler would gladly take another 3 here or a 5 here because it doesn't understand I'm initializing an array sequentially, okay? So that's why, we don't really like this kind of code if we can avoid it. So the other way to do it is a shorthand, and you can see how this is a lot shorter, because what you do is you are initializing the array while you are declaring it. In other words, when you are telling the compiler that I need an array of integers to store prime numbers, and the name of the array is prime, you can also at the same time initialize the content or the elements of this particular array. And in this case, you can also see that I do not use any numbers between the open and the closed curly square brackets. That's because this is implied by the number of items in the curly braces after the equal symbol. So in this case, we have 2, 3, 5, 7, 11. There are 5 items inside the curly braces, and that's why prime automatically has a size of 5 entries. Are we doing okay so far with this syntax? Are there any questions about this syntax to declare and initialize an array of 5 integers? Yep.
Could you use this for the initialization part in the for loop?
What do you mean by initialization part of the loop?
The first part of the for loop is like you set the number value to the thing you're counting.
Yes, you can. Yep. Okay, so obviously this is a lot better because there's also no way that I can make a mistake and reinitialize prime bracket 3 like before, because this is all spelled out sequentially, and the compiler is the one that is responsible to put each value into one element in the array sequentially. So there's no way I can make a mistake. Like what I could do here, instead of using a 4 here, I could have a typo and make it a 3. Or I can copy and paste the previous line change the right-hand side of the assignment, but without changing the index. I mean, lots of mistakes can happen when I do it this way, but much fewer mistakes can happen when I do it the other way. The other thing that's nice about this approach is if I want to extend this particular prime array to have the first 10 prime numbers, I just need to append more numbers in the curly braces, whereas in the other one, it's a big chore. I mean, I have to copy and paste a lot of lines just to make sure that I can initialize the other 5 numbers. What about characters? Okay, what about strings? So if I want to make a string of my own name, okay, this is one way to do it, because after all, a string is really just an array of characters. Okay, so I can use the same approach as how I initialize an array of integers to initialize an array of characters. Except in an array of characters, I want to not have to look up the ASCII table to find out what is the ASCII code of uppercase T, lowercase a, and so on. So I use quote T quote to basically let the compiler figure that part out by itself. Because when you say quote T quote, the compiler understands, oh, so you want me to look up the ASCII code of uppercase T, which is a handy feature. It is not 100% necessary. In other words, if I look up the ASCII code of uppercase T, I could have put that integer in place of quote T quote, and it would do exactly the same thing. It doesn't do anything different. This is just a shorthand to refer to ASCII code values. Are there any questions about this particular initialization? Do you guys notice there's one last 0 in this particular array? That's the null terminator. Okay, it has to be spelled out explicitly when I use this particular way to initialize element by element. Okay, byte by byte. What is the size of this array, by the way? What is the number of characters in name as an array? It's TAK space 4, and then AUYEUNG, that's 7 more. So that makes 11, but the null terminator takes up 1 byte too. So it actually takes up 12 bytes to store this particular array. The null terminator is just like any other characters. It needs 1 element in the array to store it. All right, are there any questions about this particular example? Yep.
What will it store if you didn't put a quote?
If you do not put the quotes around the TAK and so on, it will try to interpret TAK and so on as names of variables. And then the compiler will complain and say, hey, nobody told me anything about a variable T, and so on. So the quotes are definitely necessary because it basically says, oh, we're not referring to T as the name of a variable or that of a function. We're referring to T as a character, and I just need to know the ASCII code of that particular character. Okay. Any other questions about this code here? Okay. Yep, go ahead.
With the integer one, how come you didn't have a null terminator?
Because with an array of integers, we usually do not use a null terminator as a convention. Okay. All right. So the other way to do exactly the same thing as this one here, because you can see there's still a lot of typing. There are a lot of single quotes, okay, a lot of commas here, and I have to spell out the null terminator at the end. So the easier way to do this is to do it this way, okay? So I can say, char. In this case, you can use name open bracket close bracket. That will work as well. But pointer to is going to work. Well, okay, this is slightly different, but we'll explain the difference later. Equals to, and then this time we use double quotes. When you use double quotes in C and C++, you can specify the content of a null terminated string. In other words, whenever you use double quotes, it is automatically null terminated, which is great. Okay. Now, but there is one problem, or one big difference when you use this notation, when you use the double quote notation. When you use the double quote notation, whatever content you put into the double quotes is automatically what we call const, okay, or read only. That content cannot be changed, okay? So that means, this code, if you write code like this, the compiler will come back and warn you and say, hey, this really is not the best way to do things. because it wants to look at this instead. Okay? The way to look at this is name is a pointer to a character that cannot be changed. That's what const is saying, is it cannot be changed. Are we still doing okay so far with these concepts? How to initialize an array and how to, make a string, easily using double quotes. Yep.
So the pointer to a character that is just pointing to a single character, right? And the fact that it's an array, it's just storing.
It's pointing to a single character, but it's pointing to the first one. Right, but once you get to the first one, you can get to the second one, and so on. Because every pointer can be seen as an array. You can use the bracket notation on any pointer to refer to the next item, the next two items, and so on. Are there any other questions about this particular slide? Because this is a much easier way to declare an array and have it initialized. No questions about this? Okay, well, if there are no questions about this, we are going to write this program here, and I'm going to say const char name. Okay, so we'll just use exactly the same thing as what we have in the other code, and then we'll have an actual array of characters. Okay, so we'll have char. I'll just call it buffer, and we'll allocate 256 bytes in buffer. So in this case, buffer without a const before the char, it means the content or the elements in buffer is supposed to be changed. Okay, it's rewritable, as opposed to const char, which means those are characters, but we're not supposed to change each element. Okay, so the first thing is, if I want buffer, the array buffer, to have the same content as my name, okay, which is already in name, which is pointed to by name, the pointer to characters. One thing you might want to do is to say, hey, we can just use the assignment operation here. We want buffer as an array to have the same content as what name is pointing to. Okay, that seems to be a pretty, reasonable thing for the compiler to do, is to understand this is what we want to do. So what we'll do is we'll take a look at this program from the compiler's perspective and see if it's supposed to work. So we say g++-warn-all-c main.cpp. I don't even bother to put a -g because I'm not going to debug this program, because it will complain. It complains incompatible types in assignment of const char asterisk to char 256. There are two big problems here. The first problem is one is const and the other one is not. Okay? And then the second problem, which is more serious, is one is a pointer and the other one is an array of 256 bytes. Okay? So they're not the same. They're not considered the same. Okay, I can give you an analogy. One is basically the instruction to go get, a piece of cookie, but there might be other cookies next to it. Okay? So it's an address. That's the const char pointer thing. Okay? What char bracket 256 is a box that has enough space to store 256 cookies. These two things are not the same. I cannot just copy it. Are we understanding why the copy or why the equal symbol does not work? Question? Nope. Okay. All right. So if this doesn't work, how do we copy the content of one string into another? Yep. Go ahead.
You just make a loop that counts up to 11 times, and then you could put buffer I equals name I.
Yep, that will kind of do it. But we can also make this more general by using string copy, the function. Okay, so let's take a look at the man page of string copy. And obviously, I'm not going to retype all this stuff in my own notes because it is so easily accessible. Okay, because anything that you can actually read from man page, I'm not going to put it into my notes because you can just look it up. All right, so string copy and string and copy, they are both subroutines to copy a string from from the source to the destination. The prototype of string copy, don't mind the return type. That's really just a handy feature, so you can stack it up on string copy on top of something else. So, but when you look at the parameters, the first parameter is a destination, and the destination is, can someone describe the type of the destination? What is it?
Pointing to the character.
It's a pointer to a character, but is it a const char?
No.
It is not a const char because it does not make sense to be a const char. Because we are intending to alter the bytes pointed to by destination, and therefore it should not be a const char. Const char means we're not supposed to change it. But what about the source, which is the second parameter? The second parameter, source, has a type of pointer to a character, but this time it does have const in it, because when you're copying from the source to the destination, you're not supposed to change what the source is pointing to. Okay? In other words, const is saying read only. Do not alter this stuff. Okay? Okay, so we'll just focus on string copy for the time being and not refer to string and copy. So the description of string copy is the string copy function copies the string pointed to by source, including the terminating null byte, to the buffer pointed to by destination. The strings may not overlap, and the destination string destination must be large enough to receive the copy. Beware of buffer overruns. Okay, so it's here and it's underlined because it is important. In fact, okay, most of the time people should say do not use string copy. Okay, just don't use string copy because it does have the possibility of getting into buffer overrun issues. Okay, but as a demonstration, it's an easy function to demonstrate, an easy function to write. And that's why we're going to do it first, and then we'll deal with string and copy. That pretty much describes what string copy is supposed to do. When you go to the return value part, which is down here, it says the string copy and string and copy functions return a pointer to the destination string dest. In other words, what it is saying is whatever you pass as the first parameter is the return value of string copy, which doesn't seem to be very useful. It's like, well, I'm just copying from one string to another string. Why do I want string copy to return the pointer to the destination? Well, as I said a little bit earlier, this allows you to stack string function calls one on top of the other one. So you can put string copy as the entire invocation inside a string compare, or inside another string copy, or inside string concatenation, or inside string, which finds a substring within another string. So instead of using intermediate variables all the time, you can basically just put the invocation of one function as a parameter to another function. This allows you to do that. Okay. But at this point for this class, okay, we're not too concerned about stacking up function calls, so we'll just kind of, we'll deal with the return value later on. Our primary job is just to copy byte by byte from source to destination. So with a reference to this particular documentation, we'll go ahead and implement our own, C string copy function. So we'll go to string copy here, and we'll take a look at our main. And we'll say, this is tags. So for the time being, I'm not going to return any value because that's the easy part. So I specify void as a return type. And this will be tags own, string copy, CPY. But I would use exactly the same types as parameters. The first one is a pointer to a character. That's our destination. The second one is a const char source. And I just want to do the implementation. So I'm going to get rid of the equal symbol here. Instead, I will say tags string copy. And I will call the subroutine with, which one do you think should be my destination here? There's only one of the two variables that makes sense as a destination. Which one should it be? Buffer. Yep. And that makes the other one name. Okay. So now we'll go in here and say, okay, how do we do this? Okay, first of all, when you are thinking about implementing an algorithm, the first question is it a loop? Okay, that's the first question, because depending on the answer of that particular question, it will lead you down a different path, to make the algorithm more, spelled out. So, do you think this is going to be a loop, or can I do this with a conditional statement? it's going to be a loop because I have no idea how many bytes I have to copy from just at this point. So it's going to be a loop. Okay. All right. So every time you say it is a loop of some kind, I'm just going to use this notation here, which is not C syntax. Okay. C does not have loop or exit when. Okay. This is just my pseudo loop notation, because I need to know that okay, we're dealing with a loop here. So we have to do something per iteration. But the biggest question when you have a loop is, when do we get out? When is it considered done? Okay, that is the question. So in this particular subroutine, when do we know that we are done? You don't have to refer to the parameters or use any of those things. Just tell me, when do you think we're done? In English, you don't have to spell it out in C or C++. When do you think we are done?
We read the rest of the string.
When we have copied the entire string, okay? But when do you know that you can stop? The null terminator, okay? So we'll say, exit when we have seen a null terminator. And the null terminator would be seen in which string? Would it be seen from the string pointed to by source or destination? Source, okay. All right, okay, so that's okay. That's good as a starting point. Okay. All right, so if we are doing something like this, what do you think we're going to do per iteration? Not as an exit condition or as the body of the loop, just kind of tell me what do you think we should be doing per iteration?
Go to the next element of the array.
Copy one byte and then move on to the next, right? Okay, so for each iteration, we want to copy a byte. Okay, well that's a good idea. Okay, let's see how we can do that. So there are many ways to do this. You can keep track of an index because source is a pointer, destination is a pointer as well, and every pointer can be seen as an array, and you can use the square bracket notation. Okay. The other thing we can also do is to only look at these as pointers, and then we can use pointer arithmetics to help us move on to the next byte. Okay. So what we will do here is now to say, hey, if the null terminator is in source, maybe we can change this description to something that looks like this. Oops. We exit when whatever source points to is a null terminator. But that doesn't seem right because this kind of implies that source is a null string, which means the very first character is a null character, and that's the only time it's going to work. Okay. Well, but we can do something like this in the loop here. So in the loop body, and somebody pointed out a little bit earlier, for each iteration of the loop, we're supposed to copy one character. Is that right? Okay. So how do we copy one character from source to destination? What about something like this? That would work, right? In other words, source is a pointer to a character, const, and destination is pointing to a single character. In this direction, it's okay. The const is not an issue. So we are just copying the 1 byte pointed to by source to the 1 byte pointed to by destination. And when people look at this code, they go like, well, that's going to copy the same byte over and over and over again. And you're absolutely right. If the program looks like this, it will copy the same byte over and over again, and it's not going to exit if the string is not a null string, because we never move on to the next byte. Okay? So now the question, which is I guess the trickiest part of this particular algorithm, is how do we move on to the next byte? I'm not using an index like I using square bracket to move on to the next byte. Instead, the way I move on to the next byte is to perform pointer arithmetics. In other words, to spell out, in the longest possible way, I'm saying, hey, destination is destination plus 1, source is source plus 1. I'm not adding anything to what destination points to. I'm adding 1 to the pointer itself. In other words, if you start with the instruction to locate one piece of cookie, I'm updating the instruction to locate the cookie right next to that one. I'm erasing a part of the instruction and say, look into the next cookie, the location of the next cookie, and then the next cookie, and then the next cookie. So you can change a pointer by using an assignment operation and +1. I think we talked about pointer arithmetics in this class already. Is that right? Yep. So that is basically related to pointer arithmetic, because destination +1, which is the right-hand side of line 6, refers to, oh, I know what destination is pointing to, but that's not what I want anymore. I want the next item, the address of the next item. That's what the +1 is. All right. Well, looks like this might work, right? Because what it's saying is loop. Okay, we have a loop and exit loop. For each iteration, we copy the byte first, and then we move on, and we'll exit when the source is pointing to a null character. Well, it will kind of work and kind of not work in this case. Okay, there are some cases. The first thing we want to do is to change loop here into a different form. Okay, because in C there's no such thing as a loop and exit when, but we do have a do word here, and after do we have a while. But this is not going to work, because what is the condition after while? It doesn't matter whether it's a do while or just a single while. The condition of a while is stay in loop condition. Okay, we use that condition to stay in the loop. That's not a stay in loop condition. It doesn't look right. When should we stay in the loop? Or what is the condition to stay in the loop? When there are more things to copy, which means we haven't seen the null terminator. So not equal to 0, as you guys said, is the correct answer. Okay, so now we are almost done. It will do most parts of what it's supposed to, but not the entire job. Does this code copy the null terminator itself? It does not copy the null terminator itself, because when it sees the null terminator, it exits before it has a chance to copy it. Okay, but it has a second problem. What if the string is a null string? In other words, the null character is the very first byte of the string, and I'm copying a null string, which is perfectly okay. I mean, why can't we copy a null string? This is not going to work, because what it will do is it will copy the null byte, and then the pointer moves on to the next byte. So by the time we compare whether it is a null byte, it's not the null byte itself. Okay. So there are several ways to fix this problem. Can someone suggest one way to fix the problem? You don't have to express your solution in C code. Just a general idea is fine.
You could pre-check instead of
I can pre-check. Okay. In other words, I can check whether we are at the end before we add one to both pointers. That would be one way to fix it. In other words, I put a conditional statement around here and say only if source is not a null byte, then we'll go ahead and add one to both pointers. That would fix the problem. Because what this will do is, if we do encounter the null byte, it will copy it first, and then we won't increment the pointers. And by the time we compare source to 0, it will still be a null byte, and we will terminate, the loop will terminate correctly. In the event of we're not quite ready to quit yet, in other words, source is a non-null byte, it is not the end of the source, then we'll go ahead and increment, and that's not, it will still not copy the last byte though. The null terminator byte itself, it still won't copy it.
Wouldn't it just go forever?
No, it won't go forever. Because it will terminate when we see the null byte. And if we don't see the null byte, it will keep going. But what we do need is do something outside of this loop here, which is saying okay, we'll do one last copy here, because when we get out here, the null terminator byte may not be copied, so we'll do the copying here. So we'll say destination, or whatever destination points to gets whatever source points to, and that will make sure that the null terminator is also copied. Are there any questions at this point? Is anyone not convinced that this is going to work? Because if you're not convinced this is going to work, you kind of have to think about a counter example and say, okay, let's consider this case. Okay, the program is not going to work, and I think the program will get into an infinite loop or whatever you think it's going to do. So does anyone? Yep, go ahead.
I'm just confused. The if statement reads like if that particular spot isn't 0, then we're going to move up. Is that how it reads?
Okay, let's go ahead and read line 6 first. Okay, so inside a conditional statement, or inside the condition of a conditional statement, okay, first of all, what is source? Okay, we'll start from source itself. src is a pointer to a character. So when you dereference it, what does it become? It becomes not the address. When you dereference, when you do an asterisk, it becomes a single character, right? Okay, a single character can be, it's just an integer. It's a very short integer, right? It's an 8-bit integer. So it can be 0, it can be non-zero. Is that right? What is non-zero considered as inside the condition of a conditional statement or loop? Considered as true. Okay, so that means what we have here is really the shorthand of this. It's saying the same thing, exactly the same thing, but I'm just using a shorthand here, and to check with you guys and see if you guys can catch this when they go, oh, okay, so that's what it means. Yep.
So the first line after the do loop, say source was the null terminator, then we assign it to destination, and we wouldn't increment. So after the loop, we're just assigning the null terminator again.
Yes.
It's not really a problem.
Which is not a problem because it's overwriting a location of 0 with 0 again. So it's not wasting any byte. It's not going to access any location it's not supposed to. It is redundant. There is a much cleaner and shorter version of this, but we are going to look at this one first. Okay, so we will take a look at this one, make sure this is correct, and then we'll think of a better way to do it. Okay, and you guys will be kind of surprised by the better way because, well, surprised and confused initially by the better way. But we'll deal with this one first. This one is really spelled out and not as confusing as the other way. Are there any other questions about this particular algorithm? Any questions? Like any test cases you guys want to throw at it and say it's probably not going to work in this case, okay? Because that's how we test algorithms. No particular questions? No particular doubts about this particular program, this subroutine? Well, let's go ahead and test it. Say again?
Can you just run it?
Just run it, exactly. We'll go ahead and run it.
I wanna see what's happening.
Exactly. So when you run an algorithm like this, it kind of helps for buffer to have some kind of non-zero and non-determined content. So I guess we'll just go ahead and do it. G++ dash G dash C dash wall main.cpp, and then we'll just link it to main gdb main. All right. So we'll put a breakpoint on line 21, which is the first line in main. Run the program, and the first thing I do is to print out what is buffer. I think buffer is sufficiently uninitialized, right? I mean, there's none of my name is in it. Okay, so that's good. Okay, because we don't want it to be to have some content that resembles what it is supposed to have after the string copy. Okay, this is good. And we'll also take a look at name, and not surprisingly, name is a string and it is interpreted to be tag space onion, which is my name, and that's how we initialize it. Okay, so this is good. We single step into the subroutine. Now, as soon as we single step into the subroutine, you will notice that GDB will display the parameters of this particular subroutine. It says destination is has an address of BFFF894, and right now it is considered an empty string. Hold on a second here. We just saw buffer to be a whole bunch of gibberish. How can destination just be considered an empty string at this point? When you pass an array as a pointer into a subroutine, it has lost track of the actual size of the array. It becomes just a pointer to a character. Now, a pointer to a character is considered a string, and GDB understands what a string is. But you guys already told me that a string is 1, an array of characters, and 2, it is null terminated. Look at the first byte of buffer. What is it? It's a null terminator. So as far as string copy is concerned, who only understands destination as a pointer to a character, it is a null string. Because the very first byte is a null terminator. Hey, it's a null string. Okay. But source is not, because the first byte of source is uppercase D and then lowercase a and so on. There's a null terminator after the G, but the null terminator is not printed because this is the C convention. The null terminator itself is not really printed as a part of the string, even though it does take a 1 byte. All right, so let's go ahead and single step through this code here. Okay, source is non-null. It's going to add 1 to both pointers. It will check the next location, go back, and it's going to do this like many times. And I can check which byte is copying by just printing what is the source, and we are actually copying the second character. And almost there. There are better ways to do this. Oh, we're done. Okay, but we are not done, as in, terminating from main, because I want to check what is in buffer now. So now if I say print buffer, holy smokes, tag it is still wrong, because your buffer is supposed to only have my name and nothing else. Or is it? What is buffer? I'll give you two choices. Buffer is an array of 256 characters, or buffer is a pointer to a character. It's an array, okay? Because when we're back in main, buffer once again is an array of 256 characters. So when you print buffer out, GDB understands and say, hey, I know how big buffer is. It's supposed to have 256 characters, and that's why it prints out all 256 characters. Do you guys still remember what is typecasting? How to force the type of something into something else? Let's try to do it here, okay? Because GDB understands typecasting just as well as C and C++. So you can actually do something like this. You can typecast a buffer from an array of 256 characters into just a pointer to a single character. But when you change the type of buffer, it will also change the way GDB prints it out, because now GDB says, hey, it is just a pointer to a character. It becomes a C string. As a C string, it will only print all the way up to the null terminating character and stop right there. Okay. Are there any questions about this stuff here? Yep, go ahead.
So is the 000 after tag AL? Is that the null terminator?
That is the null terminator expressed as an octal number, base 8.
So what if the next one after the letters was the 07GF?
Then it will keep going until it finds the null terminator.
So would it print that out?
Say again?
Well,
let's go ahead and change it. Why not, right? I mean, let's do it. So we want to change this byte to something other than a null terminator, okay? So can you tell me how to do it? Yeah, you can. You just think about it. Think about it. Okay, I can tell you this. The command to change something in a C program is set var. So tell me what needs to be changed. But first of all, what is the index of that byte that we are highlighting right now?
11.
It will be 12. Okay, so, and the array is called buffer. How about that? That will refer to the byte that we are just highlighting at this point. And then you can just say, I'm going to change it to something. What do you want to change it to? Anything that is non-null is going to work. But what do you want?
A period.
Okay, so we'll specify a single dot here, using quotes. Because whenever you refer to the ASCII code of something, you have to put single quotes around it. Press the Enter key. Double check. Oops.
You did 12, it's supposed to be 11.
Oh, it's supposed to be 11? Let's see, 1, 2. Yep, it's supposed to be 11 because my first name only has 3 characters, last name has 7, plus the space. So it would be index 11, even though it's the 12th byte, it is actually as an index of 11. So let's do that again, and we definitely don't want to print it as a pointer to a character just yet, just to double check to make sure. So now we have 2 dots because it would be, accidentally change the other one. Okay, the first null terminator is now all the way over here, but between the first byte and the null terminator, some of these things cannot be printed. Okay, like ASCII code 1, ASCII code 4, they cannot be printed. And you can also see something that's kind of funky here. This one over here, that's a Chinese character, okay? And I have no idea what it means, okay? Because there are like 4,000 something of those things. So I can probably recognize, between when I was in high school, I can probably recognize somewhere around 1,500 of those characters. But because I have not used it for a long time, it's probably down to 500 now. Okay, so now we want to print it out as a string, and it will display some gibberish and all the way up to the ASCII code of 1. And by the way, \b is backspace. Okay, so if you actually print it out on the line, it would actually go back 1 space. So are there any questions about this program? So before we messed around with it, it actually worked. Okay, now that we messed around with it, the destination is no longer just my name.
Would it always have the null terminator conveniently?
Oh no.
After all the text?
It will keep going until it finds the null terminator. So that means if out of these 256 bytes in buffer, there's not a single null terminator, it will keep going after the boundary of that array until it finds that null terminator.
So should you initialize the whole array to 0?
No. No, because string copy is supposed to copy the null terminator as well. What I do need to make sure is whatever I'm copying into destination only has up to 255 bytes, not counting the null terminator, because the null terminator is going to take up the 256 byte of the array. All right, are there any questions about string copy as it is now? Okay, no questions. All right, if there are no questions, we'll go back to the program, because I did promise you that there's a better way to do this, but it would be confusing, okay? So what I'll do is I'm not going to erase what we have here, and I'll just give you the second implementation, and I will extend the screen down a little bit to the point where people in the back can still see. Can everybody still see the bottom part of the screen, especially people in the back? Is still okay, sort of? Okay, I can move it up 1 line. Let's see if that's better. Is that good? Okay. So what we'll do is we'll implement the same subroutine, but in a slightly different way, and I'll just call it string copy. There's no problem to do it like this. In other words, to implement a subroutine using exactly the same name as the one that is provided by the C library, as long as I don't do a pound include string.h. Okay, because if I do a pound include string.h, then the definition that I have here has to be consistent with whatever that one has, the other one has. Okay, so this is how we do it. This is the second way to do it. And I'll write the code first, and then we'll go back and explain it. Or I'll let you guys read it a little bit first, and then I'll explain it. That's it.
Really?
Yep, it's a one-liner.
Okay. Cool.
And the not equal to 0 is not even needed. It's only there so that the compiler won't nag at me. Because without that, the compiler will say, hey, do you really mean the equality inside here? So I'm just going to okay, fine, stop nagging. In other words, if I don't really mind the warning part, this will be it. Okay, so we are now going back to see the post increment operator that we talked about a long time ago. Okay, well, relative to a whole semester, that's a long time ago, because that's almost at the beginning, maybe the first 2 weeks of this class. Okay. Now, for those of you who do not remember, the prioritization of operators, I'll just go ahead and add additional parentheses to clarify that part, okay? Which is not going to be the main problem of interpreting this code here. So this is the actual code. So we want to find out exactly what is it doing. We're combining all of these post increment operator to pointers and dereference and all of this stuff here. So what you need to do is to figure out the ordering of operations. Okay, that's the first thing you need to do, which is already implied by the parentheses. It doesn't really hurt if you want to break it up into a quote-unquote tree type of a representation. So the top level is an equal symbol, which is the assignment operator. It copies the left-hand side to the right-hand side, okay? No, I take it back. It copies the right-hand side to the left-hand side. Okay, so it has left-hand side, right-hand side. They're kind of symmetric. The second last operation on each side is the asterisk, which is a dereference. Is that okay? Because when you look at how the parentheses are organized, the asterisk is outside of the post increment operator. So now we have a post increment, so I have to say post because otherwise it is not clear whether it's post or pre. And the increment operator on the left-hand side is applied to destination, and on the right-hand side it refers to source. There we go. So this is how the code is actually structured as the condition of the loop. Okay, how does it work? What is it going to do? Well, we start at the bottom of the tree. Okay, whenever you evaluate an expression, you start from the bottom and you work your way up. So on the with an assignment operation, do I start with the right-hand side or should I start with the left-hand side? Start with the right-hand side because it specifies the value that is being copied. So we start with the right-hand side. The right-hand side or the right-hand side of the tree starts with source because it's all the way at the bottom of this particular tree, which is also known as, by the way, a leaf. Okay, something that has nowhere to go in a tree is called a leaf. And I'm not kidding. This is actually a terminology in computer science. All the other things are called nodes. The very first one is called what? If this is a leaf, these are called nodes, and the sticks are called branches. What do you think this is called? It's called the root. You're looking at the tree in an upside down fashion, basically. Okay, and that's why root has a special meaning in a lot of operating systems. The root directory is the very first directory of the entire file system. That's why it's called the root directory. And that's also why, I guess, the system administrator in Unix and Linux is also called the root user because it is at the top of the entire hierarchy. Okay, but getting back to this one. Source is here. What is source? What is the type of source? It's a it's a pointer to a const char. Okay, that's good. It is a pointer. That's the whole point. It is a pointer to a character. So when I apply the plus plus to a pointer, what am I actually doing? I am incrementing the pointer, so it will be pointing to the next thing. That's the side effect of post increment. What is the return value? What is the value of the expression itself? It will be exactly, it's the source but before the increment, right? Okay, so when you look at this operation, you have to keep in mind there are two things happening, not just one. The first thing that happens is source is increased by 1. That's the side effect of a post increment operator. But there's also a second thing that is done. The second one is to specify a value for the expression itself. So when you look at the expression itself, the expression value is the same as the source, but before the increment. So I'm going to say before increment. Are we still doing okay so far with this code here? We talked about the post increment operator like a few many weeks ago, and we are now using it again. All right, what do I do with the return, with the value of this expression?
Dereference it.
I dereference it. So am I dereferencing the next location, or am I dereferencing the original location?
Original.
The original location, okay? So this dereference is going to dereference the original location before the increment, okay? The location pointed to before the increment. So I'm not going to miss the first byte, okay? This whole thing is not going to miss the first byte. It will start with the very first byte of the array source, okay? Destination is kind of the same thing, okay? So we look at this whole thing as an operation. It has two things that it has to do. The first one is it changes destination. It increases the pointer by 1. But it also has a value to the expression. The value of the expression is the destination pointer before the increment. Are we still doing okay so far? What are we doing with that pointer? We dereference it to specify a place to store the value from the right-hand side. In other words, whatever destination was pointing to is going to be the destination where we store the byte. But the side effect is, after the assignment operation, the destination will also increment to the next location. Are we still doing okay so far with this code? Yeah, it might take some time to process. But, well, okay, but don't do any further processing until we verify this code actually works. Right? I mean, it makes sense to basically want to some kind of verification that this works before we actually say, okay, let's go back and really look at this again. So what we'll do is we're going to change the subroutine, or change the call to make use of just string copy instead of text string copy. So this way we can double check and verify whether string copy is working or not. In other words, whether line 18 is doing what it is supposed to. Recompile. Oh, I have to recompile first. Turn on all the warnings, and you will see how it's going to complain about the equality, the single equal symbol inside the condition of a while. It's only going to be considered a warning, so it's going to be okay. No, it does not even warn about it. Oh, that's because I put extra parentheses around it already, so that's why. Well, maybe not. Yep, I did. I did put extra parentheses around it. Let's erase the extra parentheses and see whether it complains.
Zach,
Yep.
would your code not do the null operator?
So again?
Would your code not assign the null operator to this?
On line 18?
Yeah.
It is supposed to be the assignment operator, not the equality check operator. It's supposed to copy whatever we dereference on the right-hand side. It will actually copy that byte to the location pointed to by the left-hand side. Yeah, it takes some processing, okay, because we are rolling a lot of different concepts into one single line in C. Okay, does this kind of remind you of what I told you about the origin of C and C++, particularly C? Like who were the inventors of C? Why did they invent C as a programming language? This brings all of those contexts back into this class. It's like, well, it's a professional tool designed for professionals. This is the kind of power drill that you buy at Home Depot, for $500. Except, this one is extra costly because they have all the safety features removed. No safeties. Okay, let's recompile just to make sure that, yep, this time it does give me a warning, because most of the time when people do something like this, they meant, hey, does the left-hand side equal to the right-hand side? Except in this case, I really meant to copy the right-hand side to the left-hand side. But it is just a warning. It says suggests parentheses around assignment used as truth value. So what should I do? Okay, should I just leave it be, let it be, and just keep the warning message, or should I go and fix the warning message? If this is you, working in the field as a developer, as a software engineer, what would you do? Fix it. Okay. In other words, you want to make sure that the code that you compile do not give you any warning messages. Any warning messages is a valid warning that something might be wrong with your program. So if I know for sure this is what I really want to do, I'm just going to put extra parentheses around the assignment operation so the compiler does not complain about it. So the next time when I see a warning from this program, when I add more code to it, I know those things are important. I'm not just going to ignore it. But in my personal experience, I know most students will choose to ignore warnings anyway until they get their first job and take a little bit too long to finish a job, and then the boss says, well, that's taking a little bit too long. Then people will start to remember and go like, oh yeah, I kind of remember somebody said something about do not ignore the warnings. All right, so let's go ahead and debug this particular program and put a breakpoint on line 26. Run the program. Do the usual stuff. Your buffer is still a whole bunch of gibberish. Name is still name. Okay. Single step into the subroutine. Okay. And let's see what I should do here. Well, single step. Single step goes all the way out, not because it did not actually go through the iterations, but because you cannot single step in the tight loop like this. Okay, it just does not stop per iteration. But let's go back to main and check whether buffer is now changed. And you can see buffer is changed the way it is supposed to. It copied everything, including the null terminator. Are we still doing okay so far at this point about this program? Okay. So we'll take a look at the source code one last time before we move on to the next subroutine. So once again, from line 1 to line 14 is kind of the long, spelled out, but easier to understand way to implement string copy. From line 16 to line 19 is how a C and C++ developer would actually do. And there's no quick and easy way to explain line 18. That really is something that you have to spend some time on to figure out what is the ordering of operation and what each operator is really doing. Okay, that's a good test to see if you understand all of the concepts individually and also whether you can apply all that knowledge when everything is combined. Okay, like, okay, we are combining increment, pointer, and dereferencing into one single line of code. Are there any questions about line 18 other than, well, I need some more time to process it? But when you look at each individual concept, each individual operator, are there any questions about each individual operator? No questions? What about the way I broke it up on the whiteboard, as quote-unquote a tree? Okay, no other questions about that? Alrighty. It is something that you should work on, okay? If you're looking at this code, especially line 18, you go like, that's kind of, really difficult to understand. The more reason you should spend more time to understand it, okay? But you cannot just, with programming, you cannot just stare at a line of code and expect it to be understood just by staring at it, okay? What you need to do is to break it down and say, do I understand each individual component? Starting with the lowest level operation, which is the plus operator, the post-increment operator. Okay? And then you try to combine all the steps, okay? Stack it up and say, okay, once I understand this one here, do I understand the next operation? Any questions about this particular code? Yep.
As I understand it, the address pointed to by source will always overstep the null operator. Is that ever a problem?
will overstep.
It will go past it.
It will
Because
go-
it checks the previous one.
Yes.
It'll always be incrementing past.
That is correct. In other words, what you're saying is after the loop exits, source will be pointing to a location that is not a part of the null terminated string. That is not a problem. The pointer can point to anywhere, including invalid locations. If you're not dereferencing it for read or write purposes, a pointer is just a pointer. It's just a bit pattern that is not being utilized, to go anywhere. It's only when you dereference a pointer, then it really matters. Does it point to a location that is within the right range? So that's a good question. But the answer is as long as you're not doing anything with the pointer, once it gets past the end of the source string, it's okay. It's not an issue. All right. So let's go ahead and take a look at a variant of string copy, which is string and copy. So the documentation of string and copy, which is the same man page as string copy, is also here. When you look at the prototype of string copy versus string and copy, they are almost exactly the same, except string and copy has a third parameter, n, which specifies the number of bytes, the maximum number of bytes that it can copy. Now, this is a big difference, okay? It doesn't sound like a big difference, but it is. In the case of string copy, if the destination does not actually have the space to store everything from the source, guess what? String copy does not care. Okay, it will keep copying until the entire destination, entire source is copied to the destination. Is that okay? And you can set up really tricky cases where it will become an infinite loop, where the source and the destination overlap. Now think about what happens when the source and the destination overlap. So I'm going to erase this part here and show you one way to break this program in the way that it would actually crash. So let's say we specify source here, okay? And destination is going to overlap with source, and it's over here. So I'll just kind of specify this is my source, and this is my destination. When I perform string copy, not string and copy, okay, this will turn the string copy loop into an infinite loop. Why is that? Well, if you think about it, the source has a null terminator, right? So let's say the null terminator of the source is over here. That's good. I copy the first byte of source to the first byte of the destination. Second byte of source to the second byte of the destination. Third one. Hey, the fourth byte of the source is going to overwrite the null terminator. So when the copying finally gets to the null terminator, it's not there anymore. It is not a null character anymore. And it will keep going like this. It will be copying basically a repeating pattern, which is the beginning part of source will become a repeating pattern that will be copied to all the memory locations hereafter and destroy everything in the process. Okay? Are you guys convinced that this is going to happen? Nah, this is all urban myth. So what we'll do is we'll do what Mythbusters do. We'll go ahead and put it to the test and see whether this is a myth or not. Okay? So, and this really emphasizes another thing about your string and copy, why there's the importance of string and copy. So we'll keep doing this string copy thing for just one more time until we are absolutely convinced that we understand how it works. Okay. So in this case, I'm going to do some quick initialization here. So I'm just going to say this is A, this is B, and this is C. And the next one is going to be my null terminator. So in other words, the first 4 bytes of buffer is a null terminated string of ABC. Okay, pretty easy. The way I specify string copy is going to be let's copy the buffer plus 3. Well, we can do a plus 3 or plus 4, it doesn't really matter. Even plus 4, plus 5 is going to work, okay, from buffer. Okay, this is going to create the scenario that we have just displayed here, because buffer 0, buffer bracket 0 is going to copy the bracket 5. Buffer 1 is going to copy the bracket. No, this is not. It's not overlapping, so it's not gonna break it. We have to make it overlap. That would do, or even 3 will work too. Okay, this is going to work because the first byte is buffer bracket 0 is going to copy it over to buffer plus 3, and that will basically get rid of the null terminator right there. Okay, and it will just be repeating the pattern ABC, ABC, ABC until it runs out of room to copy, and then the whole program is going to crash with a segmentation fault. No one seems to believe what I'm saying here. So what we'll do is we'll prove that this is actually going to happen, and we'll do a compile g++-1 all-g-c main.cpp. Do you think the compiler will give me a warning about this? The compiler seems to be pretty naggy about little things. Do you think it will warn me about this one? Absolutely not, because the compiler does not understand string copy at all. It will complain about stuff like that, unused variable, because in this particular program, I'm not using name as a local variable. That's okay, we can let this one go. GDB main, and we'll put a breakpoint. We'll put a break. Well, I cannot really stop on line 18, so any attempt to do so is not going to be useful. So we'll just let the program run and let it crash. Oh, okay, it does crash, right? Okay, so now the question is, now that it has crashed, can we find out what's wrong with this program after it has crashed? Well, why do we even care? We already know why this program crashed, so why do we want to do a post-mortem on this particular program now that it has crashed? Well, it's because I would say, how many people in this class are planning to go through the computer science program and eventually become a developer or a software engineer, someone who's going to write software? Okay. A few people, okay? So of these people, I would say at least 25% will run into a problem that is similar to this, okay? Maybe not exactly, but it will run into a problem similar to this one. So when you run into a problem similar to this one, you only have the symptom to start with. The program crashed, and this is the symptom. What happened to my program? Okay, so what we want to do is we want to find out. The first thing I would do is a BT, which is backtrace. Now backtrace does not work anymore because it has destroyed enough content on the stack that I cannot really tell what is going on anymore. So the other thing we can do is to put a breakpoint, assuming this problem is repetitive, which means every time you run the program, you run into the same problem. We'll put a breakpoint before line 30, or before the string copy function. We just run it from the beginning, and we'll print what is buffer. Okay, it prints out what is buffer. Okay, everything is quote-unquote back to normal. But this time we'll also say what is the address of buffer, and we'll remember. Okay, write it down on a piece of paper, a little post-it, whatever you want to do. It's BFFF F894. Okay, just kind of remember that address. Then we'll go ahead and continue the execution of this program until it crashes. But now that we know the actual address of buffer, we now can say, I want to look at that address again and find out what's happening. But you cannot just say print buffer because we are no longer in main, and I guess we can, but that's not the same buffer anymore. It's not the same buffer anymore, which is not helpful. But we can print the entire address. In other words, we can say, hey, let's print 0xbFFF F894, which is what we had earlier here, right? But this is not going to work either, because what it will do is we'll print out this hexadecimal number in decimal. Okay, that's not helping me. But I remember something about typecasting. In other words, I can now say, hey, don't look at this as an integer, look at it as a pointer to a character. And that is actually something you can do in the C program as well. You can actually just cast an integer and say, hey, don't look at this as an integer anymore. Look at this as a pointer, as an address of something. Okay? So when you do that, what do we see? What did I tell you? Right? So, so what this means is, well, I just demonstrated, a little bit of technique that you can use when your program does not work, okay? And what you need to do is to use a mechanism like this to kind of examine post-mortem, okay? What happened to the memory of this particular program? If you see something like this, then you can say, hey, maybe there's a problem with a string copy, okay? There's no, either the patterns are overlapping, okay, the arrays are overlapping, or there's no null terminator in one of the strings, and it eventually leads to a problem like this. How often do you think a problem like this happens? It's just a theoretical thing that Tech talks about in his classes, but it will never happen in real life. Well, in about 30 years, if I'm still alive, you can come back and tell me whether it happens at least once in your case or not, okay? Because I'm almost certain that this is going to happen, or a variant of this problem is going to happen. So how do we avoid this from happening? What do you think? What was I about to talk about right before I talked about this problem? String and copy. Okay? So what we'll do is we'll take a look at string and copy. As time allows, we still have 3 more minutes. I think we have enough time to at least talk about it. Okay, so string and copy is slightly different, and it says right here, the string and copy function is similar to string copy, except that at most n bytes of source are copied. In other words, if you specify n to be 256, for instance, it will always stop at 256 bytes. Warning, if there is no null bytes amongst the first n bytes of source, the string placed in destination will not be null terminated. So you just have to kind of keep in mind that the last byte of destination may not be null terminated if source is actually longer than n. But it will stop. It's not going to corrupt memory forever. Okay, that is the big difference. And it says right here, if the length of source is less than n, string and copy writes additional null bytes in destination to ensure a total of n bytes are written. This is also important because what it says is it cleans up the destination. So in addition to the bytes before the null terminator that will be copied, the null terminator itself will be copied, but everything else in destination will also be zeroed out. Okay, it's not going to keep the gibberish after the null terminator. All right, so we have 1.5 minutes left. How do we implement it? Okay, now that we have n as a number, maximum number of bytes to copy, how do we get this done? Well, first of all, what do we do with this condition here? We need a second way to get out of this loop, right? We need a second way to get out of this loop when n is 0.
Or
Well, if you do an or, that means each condition can be a reason to stay in the loop. We need more ways to get out of the loop, not more ways to stay in the loop. So we need an and. Okay, we need an and so that we have more reasons to get out of the loop. So we need n to be non-zero to stay in the loop. And then for each byte that we are copying, we're going to say, okay, let's decrement n. For each iteration, for each time we copy, we say decrement n, so n eventually will become 0 if there are not enough bytes in the destination. But there's one more, there are more things we need to do, because we also have to say, as long as n is non-zero, we have to do something else. We have to say the rest of the destination also needs to be initialized to a null terminator. And in this case, I can use n plus n minus minus in the loop and not use anything outside of the loop. So what this will do is it's going to copy the source to the destination. If the source is shorter than n bytes, it will also copy a whole bunch of null terminators into the destination. Well, let's check out whether this is going to work or not. Okay, the first thing we want to do is we'll say, okay, just looking at the code, is it going to copy a null terminator or null string by itself without any problems? A null string starts with a null terminator, which means it will copy the null terminator into the destination, and it will decrement n by 1, okay? And by the time it gets here, n is already decremented by 1, and it will still work for a null string. Okay, let's check it. Let's check this one here. Okay, let's see whether this kind of messed up function call is going to work. And in here, we'll specify 256 minus 4 as the size of the destination. We'll copy up to this many bytes. The program did not crash. It went through the function call just fine. And we want to find out what is in buffer. Well, they're all ABCs, but the program did not crash because we did stop at some point. Okay, n becomes 0, and we stop even though we have not seen the null terminator. This is one way to test it. We'll do another one to test it, and this time we'll use name. All right. And we'll specify 256 characters in buffer. There we go. So what will happen this time is it will copy my name into the destination, which is buffer, but it's not just going to copy text, space, onion, and then a null terminator. It will also zero out everything else in buffer into zeros, into the null terminator, as the documentation specifies. So go ahead and check this out. 2, run the program, print buffer. Uh-oh, it didn't work. Oh, I know why. You can see that it put a null terminator here, and then another one here, but then it did not put null terminators throughout the entire buffer. Okay, let's fix that. Well, there's a reason why it didn't do it. The reason why I didn't do it is because of this being considered a part of the condition. What does that do? Okay, let's examine this condition here, or this expression here, and see why the program did not copy all the zeros throughout the buffer. Okay, this is an assignment operation, right? Single equal is an assignment. This is the right-hand side of the assignment operation. This is the left-hand side of the assignment operation. That's not the issue. What is the value of this as an entire expression?
0.
0. And 0 and whatever is 0 is always false, right? So that's why it copied one single byte, extra byte of 0, and then it stopped. Yeah, that's not what I wanted to do, but I'm too lazy to really make a whole lot of changes to this code. So what should I do here? How can I ignore this one here? How about that? That would do it, because what this does is it will evaluate the first expression, but the value of the first expression is completely irrelevant. It will just kind of toss it away, because there's a second expression here, and the value of the second expression will be used to determine whether we should exit out of the loop or not. Okay, so I think that should fix it. And we'll recompile, relink, go through the debugger again. put a breakpoint on line 32, run the program, create buffer, and now it does work. So, any questions before we end today's lecture?
Do n and the size of buffer need to be the same for that to still work?
It can be
or-
smaller than, but it cannot be greater than. Should not be greater than.
Okay.
But that's a good question. You know, how do we know the buffer has exactly 256 bytes? Well, you know, this is a bad way to write this program because I can also do this. Size of is an operator. It tells you how many bytes are allocated to whatever is in the parentheses. So this would be a much better way to do it. Okay. All right. Well, this is going to conclude today's lecture. You still have your homework assignment to work on, and I'm hoping that most of you have at least started on the homework assignment, or at least watched the video that I recorded on Monday, because I did some work with as a hint, as a double loop. Okay, so that would be a good starting point to start thinking about it. So I'm going to stop the recorder, and if you